couple of weeks, and then we'll switch to optimization. Okay, all right. So partial differential equations, and you'll remember there are more than one independent variable. That's the characteristic of this. Okay, and there can be more than one dependent also, but we'll consider one dependent variable. But there may be more than one dependent variable. Okay, and you will. So, for example, we are going to call independent variables. Let's think of the simplest case of more than one is a 2. Okay, that's the simplest. That's the lowest number of independent variables needed to have a PDE, right? And let's call them x and y. And dependent variable I'm going to call u. Okay, so you have a PDE that expresses u and its derivatives, which could be all these kinds of derivatives, which could be a first, second, and if I have a higher order derivative, it would be combined. It will be like a combined derivative, like x, y, x, or x, y, 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 x, x, and so on, etc. Okay, so all such terms will appear, and that's a general form of the PDE that we may find. Okay. All right. So, and then solution will be essentially you want to find u as a function of x and y. Okay. So that will be your after solving this, you will find a function unknown, or which is a dependent variable as the functions of independent variables, right? There will be, of course, initial conditions and boundary conditions. Okay. All right. I'm going to start with the simplest scenario, which is first order. Okay, so simplest case, the first one, simplest case would be first order, okay, linear, okay, I think that's it. So linear, okay. So linear would mean that this function that I have up here will be a linear function of f, will be a linear function of u and its derivatives. Okay, and so the form that I'm going to write down, I already did that in the last class. So form was a can be a function of x and y, ux plus b uy, okay, equals to c naught u plus c. Okay. All right. So this is the form that I'm going to write. This is the most general kind. So here also again let me explicit. C0 and C1 can be functions of x and y. A and B is a function of x and y. Uy equal to C0 of x comma y. U plus C1 of x. Okay. So that would be your general form. Okay. General first order linear PD, because you see it's first of all it's linear because you have all the terms u, ux and uy appearing in the expression where in the equation where these are linear, right? They are not exponents of them. Okay, so there are no nonlinear terms, no product terms. Okay, and it's first order because the highest derivative over here is the first derivative, which is the first order. Okay, so that's first order, and so I have started using Wi-Fi. Just a second, guys. Wi-Fi use कर रहा हूँ. या अभी तो मैं वही करूँगा. आपको मैंने कॉल किया 2 बार. सर मेरा लेट हो गया. आप अभी क्लास करिए, सर मेरा नंबर आप कॉल कर दिया. मैं लोकेश को कॉल किया, वो अकाउंट सेक्शन कॉल हम अभी क्या करेंगे, आधा घंटा है क्लास, आधे घंटे के बाद उसमें क्योंकि मैं लैन में नो इंटरनेट दिखा मैं फोन है. और उधर भी काम नहीं करो, उधर Okay, let me continue then. All right, so okay. All right. Okay, so that is the general form, right? Now, now, so when you solve this, so first of all, I probably you're convinced that this can be the most general form. There's no other term that would need to be included in the most general form of first order linear PDE, right? So I have simplest situation when I have two independent variables x and y, derivatives of the first order are appearing, and that's a linear equation, right? You have to keep in mind that these things a, b, c, c0 and c1, etc. These are coefficients, right? These are coefficients, and they could be non-linear functions of x and y. Okay, they can be non-linear functions of x and y. Okay, that would not make the equation non-linear. Okay, remember non-linearity is only in terms of dependent variables, nothing else. The dependent variable are u and its derivatives, of course. So only non-linearity only appearing because of those terms. Okay. All right. So now, when you solve this, you get u as a function of x comma y. Okay. Okay. So this would be a function I'm going to let's call this z. Okay. Okay. So when you this would be your solution. Okay. Solution would be some function z of which I'm going to represent as u of x comma y. Okay. Now, why am I writing it this way? Okay. So the reason is that I'm going to define. So I'm going to basically motivate a geometrical interpretation of geometrical representation of the solution. There is a way to visualize, and thereby once you have a geometrical representation, then you can proceed to find the solution. Okay, it becomes easier to visualize and easier to understand the way solutions can be found. Okay, so what is it? So what we are going to do is I'm going to write down z equals to f of x comma y. Okay, that is my solution. Okay, and if I define z to be a third axis, okay, so x, y, and z, okay, then this would become a equation of surface. Okay, so you see, remember always, if you have 1 degree of freedom, that would be a line. Okay, a line. The 2 degrees of freedom, that would be your surface. 3 degrees of freedom, that would be your volume. And your higher degrees of freedom, that would be hyper space volume. Right? So okay, so some kind of imaginative space of higher dimensions which our senses cannot perceive, but you can imagine, like if you had a 4-dimension, then the volume in that particular space would be your object that would be having 4 degrees of freedom around it. Okay, so if you have any variable which has 1 degree of freedom, it can be, and it will be representing if you have no degrees of freedom, that's a point. Okay? 0 degrees of freedom, maybe I can mention here, 0 degrees of freedom, that would be a point, fixed point. There is nothing you can do. There's a given result. Okay, there's a given point that will have 0 degrees of freedom, right? So here, for example, if I am writing f of x comma y comma z equal to 0, okay, this is what is this? I have 3 number of variables, okay, and out of that I have 1 equation. That would mean I have 3 minus 1 degrees of freedom. Okay, And that would be basically a surface. Okay. So, or other example could be, for example, if I have a two-dimension, let's say x and y, and if I have an equation of f of g of x comma y equal to 0, that's a line, right? That's a curve. So y equals to fx is a curve, okay, which is essentially f of x minus y equal to 0. This you can take to be g of x comma y. There's a question. About number greater than 3, don't worry about greater than 3. So that would be unnecessary. That we will never be concerned about. Well, what I said about number being greater than 3, it's called hypersurface. Okay, it's called hypersurface. So you can have more than 3 dimensions. Then any, if you have degrees of freedom larger than 3, then you cannot imagine it. I mean, visually you cannot visualize it, but you can imagine. It's considered. It's called hypersurface. That's all. Okay. So it's a region, a domain in something known as manifold. Okay, so don't worry about it. It's simply an extension of so like it's an extension of measure in higher dimensions. For example, if I have one dimension, you measure things by length. If you have two dimension, you measure things by area. If you have three dimensions, you measure things by volume. If you have four dimensions, what would you call it? Well, we do not have, so we call it hypervolume or something like that. Okay, so it's a measure in hyper dimension space. Okay, it's not a, there's nothing to be visualized here. It's just a mathematical extension of the same concept. Okay, that's all. Okay, so here, so for example, this equation that I've written up here, okay, or the solution would be, I'm going to write it like fx comma y minus z equal to 0. Okay, which I can write down as, let's say, capital F of x comma y comma z equal to 0. Okay, and this is surface in 3D space, right? So what it tells me is that for every x and y, every x and y, for every x and y, I will have a unique z. Okay, so for every x and y I choose over here in xy planes, okay, there will be a unique z. Okay, and therefore you will form some kind of surface in the three-dimensional space. So for every x and y I choose up here, I'll have some point over here. Okay, so just take the collection of such points, you'll form a surface. Okay, so this would be your z equals to f of x comma. Okay, so this is also called solution surface. Okay, this is referred to as solution surface or integral surface. No, integral surface. Okay. Now another important thing about surfaces, which you may be probably aware. Can anyone tell me, if I have a surface given by f of x comma y comma z equal to 0, so equation of surface, then which way does the normal to the surface point? Can you tell me, if I have this information provided, that means if I know function f and I'm supposed to construct a vector which is pointing normal to this surface at any point, how may I construct that vector? Can anyone answer me that question? It's something that you must have studied earlier. I just want to refresh your memory. If I have a function given by f of x comma y comma z, and I collect all such x, y, z's so that this function becomes equal to 0. When I do that, I'll essentially define this condition will lead me to a surface. Okay. Now my question is, once I have that surface and I am standing at any point radially, no, not radially outward. It's not radially. I want a point. See, you understand the difference, right? So you have a, let's say, I have a surface that may look like this. Okay. the surface that may look like this. Okay, something like that. And you have, this is your, let's say this is my x-axis, y and x, y and z are these. Okay, and this is my surface, okay, which is given by f of x comma y comma z equal to 0. Okay, now my question is, at any point, for example, if I choose here, the radial direction would be this direction. Radial would be, just think of this as origin as a center, and this would be a radial direction. But what I'm asking here is, I want to construct a vector which is normal to this surface. I want to have this vector, which is, if I choose any tangent at this point, okay, it will be normal to any of the tangent I can construct over here. Okay, so this would be my n cap. Okay, so I want the, yeah, good. So someone has answered gradient of that function at that point to find out. Absolutely right. So gradient is actually the normal. So del f is normal to the surface. Thanks, Abhishek. Yeah. So, do you know why? Why is why? How do you know that it's a normal? It should be normal. How can you convince yourself? If others don't remember it, can you recall why is it normal? Well, I can quickly justify this. You imagine, suppose I have if you are at any point x, let's say this point coordinates are x, y, and z. Okay, I'm standing here. Now let's say if I move slightly in some direction, okay, some arbitrary direction. So I have x, y, I'm standing at at x, y, z, and my value of the function is f of x, y, z. Right? Value of the function f of x, y, z. Now, which is 0. Okay, so value of the function is 0 at that point. Right? Now what I do is I change my position arbitrarily a little bit. I can change x, y, and z arbitrarily. Well, I cannot choose x, y, and z arbitrarily. I have to move it so that I have to remain on surface. That's why it's a surface. If I was able to move all the three components independently, I would have explored a volume. But since I know that I have to move in a restricted manner, so that I have to make this one, I have to move in such a manner that this value of the function remains 0, then I'll be moving on this surface only. Okay? So let's say I'm moving on the surface, so that x goes to x plus delta x, y goes to y plus delta y, and z goes to z plus delta z in such a manner that f of x plus delta x, y plus delta y, z plus delta z, that is still 0. That means I'm moving on the surface only. Okay, which would mean I have moved along one of the tangent directions on the surface at this point. Okay, because tangentially, if I move, so that f of x, y, z is not going to change. It will remain 0. Okay, so if this is 0, that would mean what? This is equal to del f. First approximation, the limit delta x tending to 0, this would be del f by del x delta x over del f by del y delta y plus del f by del z delta z. Okay, that would be 0, right? Now this I can write down as del f by del x I cap plus del f by del y j cap plus del f by del y del z k cap dotted with delta x I cap plus delta y j cap plus delta z j cap, that is equal to 0. Okay. Now I know that this vector delta x I cap plus delta x I cap plus delta y j cap plus delta z k cap, that has to be so remember, what is this? This is basically movement. Okay, so change in position by how much I have moved from the original point. Okay, so that is such that, remember, I'm moving on the surface. This should be parallel to the tangent, right? Because I have to retain myself on the surface. Therefore, I have to, in any way, in the limit when these numbers go to 0, I am moving along a tangent to this point, tangent to the surface at this particular point, which it can point any direction, but whatever it is, it has to be tangential to the surface. And this is tangential direction. Okay, and this dotted with this vector is 0. That defines that this has to be parallel to normal vector. Okay, so therefore this is nothing but del f. Okay, so del f is always parallel to normal vector at any point, on a surface, right? Okay, so uh, so now what do I have here? In our case, uh, f of x, y, z has a particular form which is expressed in terms of solution uxy minus z, that is equal to 0. Okay, this condition has to be satisfied. Okay, so in my current, when I'm trying to establish a geometrical analogy of the solution, okay, I notice that my f of x y is a surface that is described as a particular form which is given by this the capital F of x y z has a particular form that looks like this. Okay, and this is set to 0 to get the solution surface, right? So it's not any arbitrary function, right? So here there is a two independent part. One is one is purely a function of x and y, and minus z. Okay, minus a linear z. Okay, that's all. So now, so uh, so if I have to construct a del normal to this surface, okay, so normal to f of x y z equal to 0. Okay, that would be basically given by del f, okay, which would be ux cap plus uy cap minus 1, right? Because if this is taken as f of xyz, okay, then the fx will be equal, or fx will be del f by del x would be equal to ux of y, which is del f by del y, will be equal to uy, and for z, that is del f by del z, that is equal to minus 1. Okay, so this would be, I'm going to write it like other notation where I just collect the component function. Okay. So this is my del. All right. Okay. Now let's look at the equation, our differential equation, first order linear PD, PD in two variables, two dependent variables. Okay. The form that is the most general form that we had was I decided to write it like ux comma y ux plus e of x comma y uy equal to c naught x comma y u plus c1. Yeah, right. Thank you. Of course. That should be, of course. Mhm. Okay. Okay. Is that all right so far? So this is my equation, the governing differential equation, right? And I'm going to do a little mathematical jugglery here, little bit. What I'm going to do is I'm going to write this as, well, maybe I can take this on left hand side. I will not write, henceforth I will not write explicit dependence on x and y for the coefficients. Okay, I'll just write a. But remember, you have to keep in mind that these are still functions of x and y. Okay, a ux b uy plus minus c naught u minus c1 equal to 0. Okay. Now, what I'm going to do is I'm going to write this as follows. Left hand side expression, I'm going to write it as a dot product of two vectors. One I'm going to choose as the del f vector, which I defined over here, which I found over here. Okay, so ux, uy, okay. What do I get on the left hand side? You can check it. It can be written as a, b, and then c0, 2 plus c1. If I define a vector which is ai plus bj plus c0u plus c1k, okay, then dot product of that will be a into b, a into ux plus b into uy minus c0 minus c1, c0u minus c1 equal to 0. Okay. So having written this, now I know that this would imply a vector defined as, so in general I can say the vector, any vector parallel to the vector, any vector that is parallel to the vector A, B, and C0 plus C1. Okay, these will be the x, y, and z components of that vector. Okay, will be what? Will be it's perpendicular to the normal vector, right? This is the normal vector to the surface, so this will be tangential to the solution surface. Okay, so once you have constructed the solution surface, then I know that if I can identify any vector which is parallel to this number, these numbers at any, remember these numbers will change as you change x and y. But as you change x and y, A will change, B will change, C0 will change, U will change, C1 will change. Okay, so if you know x and y, then as you change at any x and y, if you can construct a vector which will be having these components, that will definitely parallel to the tangent of the solution, tangent along the solution surface, right? Is that all right? So I hope that this much geometry should be fine. Okay, you can deal with this, right? Okay, so this is tangential to the solution surface. Therefore, now we are going to remind you something very similar to the definition of streamline. If you recall a streamline, uh, if I if you have any vector, okay, so so if you have any vector, right, there is a parametric representation of a vector. So remember, this is x, y, and z, okay, and actually. Let's do this. Now, okay, so just pay attention here that these quantities, okay, as I change my x and y, x and y, these quantities will change. Okay, that would mean that that particular tangential vector is actually changing. Okay, so you essentially what you're going to do is you're going to derive, there's a tangential vector over here like this. If you change xy slightly, tangential vector may change like this, and then it may change like this, and it may change like this. I do not know, but I'm just giving you a representation, a possible representation, right? This is like a streamline. Okay? At each point, I have a tangential vector defined, which may be changing with x and y. Okay, as I change x, y, okay, then in the solution surface, okay, I my tangential vector will keep on changing, and I may find out that probably, well, depending on how you change x, your this tangential vector will keep on changing, right? So that will be basically you're moving on this surface, okay, along a curve. Okay, so this will be like moving on a surface along a curve. Okay, so as x and y change, okay, the tangential vector direction changes. Okay, depending on how you change x and y, your tangential vector accordingly change. Okay? Therefore, basically what you're doing is you're moving on a curve, moving on a particular curve lying on that surface. Lying on the surface. Okay, so I just showed for example, if you, for example, if you had, let's say, if you decided to move xy linearly from this direction this way, your curve may look like this. If you decided to come here, if you decided to move this way, your curve may look like this. Okay, but whichever way you change your x and y, accordingly your tangential vector is going to change, and you are going to trace a curve or trace a path on this surface, right? So path will be traced. Okay, so curve or path will be traced. Okay, and that path or the curve will be given by these three numbers. Okay, at each x and y, I have, so for example, over here I have some a, b, and this number evaluated. From this, I know, okay, I'm going to move this direction. Let's see. I slightly move away, okay, and then I say that, oh, I'm going to move in this direction, and so on. So that way you can actually place it down. Now, that particular curve, okay, remember, you all probably know parametric representation of a curve. You remember that? How many of you remember this? Parametric representation of a curve. So just to give an example, you can have, for example, y as a function of x, okay, and that will be a curve, right? Y equals to fx, okay. Yeah, right. Well, r and theta is just an example, but yeah, that's the same thing. Y equals to fx, right? You can define parameters. So, for example, let's say a fly or an ant moves on this curve, okay. So, and with it, you can imagine that you are tracing its curve, and then eventually, when the ant goes from here to here, you have traced the curve. But the same information can also be represented if I had tracked its velocities in x and y directions. So say if I knew vx and if I knew vy, okay, then I know I can also, so that would be dx by dt, and this would be dy by dt. Okay, then from these two information I can also find out the curve. Okay, okay, how the curve evolves with time. Okay, then that information, so this shape of its path, okay, when I just draw this path, I do not know how this path has evolved. But when I write it like choosing time as my parameter, so this would be like time is chosen as parameter. Okay, what you do here, you have, if you know x as a function of t, okay, from this equation, if I know vx and vy, I can find out x as a function of t and y as a function of t. Okay, and in between these two, I can eliminate t to get y as a function of x. Okay, that will be exactly the same as the equation of the curve. Okay, so either you give xt yt information or you give directly y equals to fx. Okay, so when you give x as a function of t and y as a function of t, rather than giving a direct expression for the curve, if you represent it like this, x as a function of t or y as a function of t, then you are actually giving a parametric representation of this curve. Here I have chosen the parameter to be t, but that need not be the actually case. You can, for example, you can choose another way to define another different parameter could be, for example, at any point I can define, uh, let's say a polar angle. So suppose at this point my angle of the angle would be, for example, or I can define the length along the curve as my parameter. Okay. So say as curve is traced, your L changes, total length along the curve is changed. So I can choose that as my parameter. Okay. So if you write x as a function of L, if you write f as a function of L and y as a function of L, if you know these dependency, then you can again get y as a function of x. Okay. So it depends on what you choose as parameter, depends on the nature of problem or nature of information that you have at hand. You can define a parametric representation of a curve. Okay. Um, okay. You must be having class now, I suppose. So I have exceeded my time limit, so I will stop the class. We'll start from here. Okay. All right. Any question? I will stop the class. You have